Welcome to the next video on energy exchanges and chemical reactions. Hopefully you watched the videos from thermodynamics made by some lovely people at the Royal Institute. They tend to do a good job at describing everything physics / chemistry related. After all, most of those people have PhDs, so I hope they do a good job of that. So if you watch those videos, then you probably heard them use the term enthalpy. Enthalpy is a term that we use for energy inside of a chemical reaction. It kind of describes the overall kinetic and potential energies of the system. So in this course, we're going to refer to delta H as enthalpy, and we use that delta because that signifies that there has been an overall change in energy. You guys have probably used that in grade 10 with your change in time. You're going to use this with your change in enthalpy, change in temperature. You probably did this with change in velocity in grade 10 as well. So delta is just it just means your overall change. That's all. So when we have a change in energy that is positive, it just means energy is absorbed. All right, it has taken some surrounding energy from around it and has introduced it inside the actual chemical reaction themselves. So you might see this in the melting of ice or common chemical reaction you've probably done at home is combining baking soda and vinegar to make those volcanoes and that chemical reaction. That's actually an endothermic reaction. So what you see in an endothermic reaction, mathematically, yes, your enthalpy is going to be positive, but you're going to see, or at the very least feel, the chemical reaction get colder. And the reason why it's going to get colder is because it's absorbing energy from the environment. And so therefore it's going to make the environment around it feel a lot colder. If you're in class, remind me, we might actually, I might, depending on the time that we have, I might quickly just whip something together and let you see this for yourself. But if you're at home, just put a thermometer in a cup and then dump in some baking soda and some vinegar, and you'll probably see the temperature decrease a little bit. And that's a good example of an endothermic reaction. Exothermic reaction, I know you've probably lit a match. So in an exothermic reaction, energy is released. And so when the energy is released, the surrounding environment gets a lot warmer. But what that means internally is that the chemical reaction, or the system for that matter, has lost energy because that energy is now out in the environment. And so again, the environment gets warmer, but the internal energy has been lost. And so therefore, exothermic reactions have a negative enthalpy. And that can be very confusing with students because right away they'll think, oh, it's gotten hotter, so energy must increase. Says, well, the energy outside the chemical reaction has increased, but inside the chemical reaction, it has lost energy. And so therefore, mathematically, you'll solve for a negative enthalpy value. So that can be somewhat confusing. Now, this is the type of chemical reaction I guarantee you've probably done. I guarantee you probably lit a match at some point, or at the very least, you've watched fireworks, or seen a candle burning. So those are probably the most common examples of exothermic reactions. Most of the chemical reactions you do in your labs in class end up being exothermic reactions. The next lab that you're going to do is specifically an exothermic reaction, so you can see that firsthand in the coming few classes. So the way we'd write and add enthalpy into our equation, you just tack it on. So if it's an exothermic reaction, the enthalpy is added on the product side of the chemical reaction. So here, if you actually make copper 2 chloride, you would take 1 part copper and 1 part chlorine, add them together, and when you do add them together, it will release about 220.1 kilojoules of energy for every mole of product that you create. So, and this is because you have leftover energy after the fact, once you're done combining the actual two chemicals together. And so that leftover energy spills out into the outside world. Now, it doesn't necessarily mean it's on fire. I guess this is a misleading picture here. Doesn't mean it's actually on fire. It just could mean it got warmer. The outside environment got warmer. And again, you're going to see this coming up right away. So if you actually take out the enthalpy from the chemical equation, you would write it down as, in this case, it would be the heat of formation, because we are forming the product copper 2 chloride. And so in this case, we know that it would be an exothermic reaction, so we'd have to include the negative. So your heat of formation here would be 220.1 kilojoules. So kilo again means 1,000. So it's 220, 100,000. Sorry, 220,100 joules. Oh, that was a mouthful. We tack on this per mole here when it's written in delta H notation. When it's part of the chemical equation, you'll notice there's no per mole there. And that's mainly because we don't write down 1 mole of copper. Like you don't see this in part of the chemical equation. We mainly don't write 1 because it's 1. But even if it was 2, we wouldn't write 2 moles. If it was 5, we wouldn't write 5 moles. We tend to not use the units when it comes to chemical reactions because the gods of chemistry said no. So when you actually write your enthalpy off to the side, you must remember that this is all based on the number of moles. If I doubled this chemical reaction, I would have 2 moles of copper 2 chloride, and so I'd have 440.2 kilojoules for every mole of substance as far as its energy is concerned. If I look at water and I wanted to show, okay, well, I know water is, liquid water has negative 285.8 kilojoules for every mole. So if I actually did the equation to create water, I would need 2 parts hydrogen for every 1 part oxygen. That will create 2 parts of water, or 2 moles of hydrogen for every 1 mole of oxygen will create 2 moles of hydrogen. Now, if I tack this on, my enthalpy, I know it's exothermic, so it goes on the product side, but I had to multiply it by 2 moles because I have 2 moles of water in the end. So 1 mole of water would have released 285.8 kilojoules. 2 moles of water is going to release 571 0.6 kilojoules. So you have to be proportionate. So this is one of the only times that you're allowed to break some rules of chemistry. Typically, we like some whole numbers in our balanced chemical equation. If you're trying to represent the enthalpy for 1 mole of water, like I have here, but off to the side, you would actually need to divide everything by 2 in order to represent this heat of formation chemical equation with just 1 mole of our actual product. So that means if you want to have 1 mole of water, you just divide everything by 2. Everything gets divided by 2, including our oxygen here. And we end up with a fraction in my actual balanced chemical equation. Now, we typically only do this when we're involving enthalpy. If there's no enthalpy involved, we usually don't bother with these half fractions or just fractions in our chemical reactions. We like whole numbers for the most part because it's just easier to deal with. But this is what it would look like if you were trying to balance it off for 1 mole of your desired product. Now, it's not always going to be the product that's desired for 1 mole. Sometimes like, well, what if you only had 1 mole of hydrogen? Well, in this case, then you would have just did the same thing. But sometimes you can pick on some of the reactants and represent one of the reactants with the amount of energy released or absorbed, depending on the situation, for your reactants as well. So when it comes to endothermic reactions, it's the same idea, except you're not adding on the enthalpy on the product side, right? So there's nothing there. You're just adding on the enthalpy on the reactant side, because with endothermic reactions, energy is absorbed, and so therefore the surrounding environment gets colder because it's taking energy from the environment, and so therefore that energy has to be added on to the reactants. And so your enthalpy gets put on the reactant side. In this case, if we're trying to make carbon dioxide and hydrogen, we would just have to react carbon with water and a little extra juice. So a little bit of extra energy, and we can actually make carbon dioxide and hydrogen gas. So endothermic reactions, the enthalpy gets put on the reactant side. And again, if you separate the enthalpy from the chemical equation, you would have to write your delta H, your heat of formation, as a positive value to indicate that it is endothermic. Now, once again, if it's written outside of the chemical equation, so it's not part of the chemical equation here, you'd have to write it down as a kilojoule per mole. If it's part of the chemical equation, all the numbers out front are moles, and so that means you would have multiplied it by so many moles, and therefore you wouldn't have the per mole as part of the chemical equation. So sometimes it does get confusing. That part's not that big of a deal, but that's kind of why it's written the way it is. Some of your practice problems will consist of just getting familiar with writing the enthalpy as part of the chemical equation or taking it from the chemical equation. So I think for the very first question, there's A, B, C, D, E. I think A, B, C, D, E. I think it goes to E. Might go to F. You'll have a situation like this where it says for each of the following, rewrite the equation in delta H notation for 1 mole of the underlying substance. And so the underlying substance here is our carbon monoxide. So if we take iron 3 oxide, add it to carbon monoxide, it should produce carbon dioxide and just iron. And it's going to release 25 kilojoules of energy. So this is an exothermic reaction because it's on the product side, the enthalpy is on the product side. And so if we're trying to rewrite this equation for 1 mole of the underlying substance, we'd have to divide everything by 3, including the energy. All right, so if I want 1 mole of this, I would need to divide everything by 3. So and that basically looks like this. We end up with 1/3 of a mole of our iron 3 oxide. We end up with 1 mole of carbon monoxide, and that's going to produce 1 mole of carbon dioxide, 2/3 of a mole, because again, 2 divided by 3 doesn't balance out. Don't turn this into a decimal value. Don't change this to 0.6 repeating. Just leave it as 2/3. 2/3 is a nice fraction. Try to keep numbers as neat as possible. And, well, you can't get around this. 25 divided by 3 is going to be 8.3 repeating. Very often, I would just call it 8.3 and not bother with the line over top to indicate that it's a repeating decimal. But I put it on there for this video. If we were to write the enthalpy separately, it would be a negative 8.3 repeating kilojoules for every mole. So that's what the delta H would be on its own. And if we took it away from the actual equation, I'd end up with these ugly fractions as part of the actual chemical equation with delta H separated from the lot. So you just have to do stuff like that as part of your actual practice. You might have to go backwards and put it back into the chemical equation. So in a case like this, you have iron 3 chloride undergoes a decomposition reaction, and it produces iron 2 chloride plus half a mole of chlorine gas. So I have a positive delta H here. Oh, forgot to put the F and the degree symbol. Well, that's fine. Sometimes I get some typos here and there. So all that little degree symbol means is we're at standard temperatures and pressures for the most part. So I have a positive here, so it means we have ourselves an endothermic reaction. So when I put my enthalpy into my chemical equation, it's going to have to go in my reactant side. So when our iron 3 chloride undergoes a decomposition reaction, energy is absorbed from the environment. So it also says I need whole number balances. So in order to get whole number balances, I'm going to have to look at my chemical equation, look at the fraction, look at the denominator. So I have a 2 in the denominator. So if I multiplied everything by 2, I would be able to get rid of that fraction, and then I just have whole numbers in my chemical reaction. But I have to do more than just multiply my chemical reaction. I also have to multiply my enthalpy. So when I do so, I'm going to have to apply enthalpy inside the chemical reaction, then multiply by 2. And of course, technically it's 2 moles. And so that's why the mole per mole gets canceled. And it looks like this inside my chemical reaction. I end up with 2 moles of iron 3 chloride. 173 times 2 is 346. So now I have 346 kilojoules of enthalpy added to my iron 3 chloride. And it produces 2 moles of iron 2 chloride plus just diatomic chlorine gas. So you'll have a couple questions like that. Oh, it's not A, B, C, D, E, it's just 1 to 5. I misremembered. So I have some questions. 2 questions for the most part, or 2 sections, I guess. 1 section there, second section there. And that's based on the 2 example problems that I just did. Those ones should take you maybe 10 minutes if you're dawdling. You're just doing basically what I did in class. And I think in your notes even has the example problem. So you should have a rough idea of how to do that. The second part of this video is going to talk about actually using the heat of formation to determine how much energy is going to be released in a chemical reaction. And so that involves using a chart. So charts are lots of fun because you don't have to memorize any of the numbers. You just have to know what page this chart can be found on. So inside of a chemical reaction, if chemists know how much energy was required to actually make every single individual compound, Um, they can determine how much energy should be absorbed or released just by combining all of their energies together, because we know energy cannot be created or destroyed, it can just be rearranged. And so when you mix up some chemicals, if there's a chemical reaction, um, and there's any leftover energy in this chemical reaction or any energy that's needed for this chemical reaction, it can be determined by looking at the overall heat of formation. So the equation to determine that is to figure out all of the heat of formation values necessary for our products and all the heat of formation values necessary for our reactants. And so we look for the total, sigma here, that's the sum of the enthalpies of our products, and we subtract the enthalpies of our reactants for every chemical reaction. And then we can determine whether or not we're going to have an exothermic reaction or an endothermic reaction. So when you're doing the math for this, I guess this should have been the last slide, but when you're doing the math for this, do pay attention to the state of your chemical. Sometimes they're in different states, so solid, liquid, or gas, and that means they would have different heat of formation values. Also pay attention to whether or not their enthalpy is going to have a positive sign or a negative sign, and what that means when you actually put that into your chemical equation, because remember, you're doing an actual subtraction. And so sometimes that can mess up a few of your results. And really do pay attention to make sure that you actually put your products on the left-hand side. In a chemical reaction, it's always your reactants produces, you have a few reactants in there and they, combine together or rearrange and you end up creating your products. So the reactants are typically on the left-hand side of a chemical equation. Products are typically on the right-hand side of your chemical equation. But when it comes to the heat of formation, we're going backwards. Products are on the left, reactants are on the right, so they crisscross. And students have a lot of trouble with that. So one thing to note, this is kind of the most important one, the heat formation of elements in their standard state are 0 and they do not actually appear on the table. So if you have lithium, for instance, and lithium is part of your chemical reaction and it's just lithium reacting, you're not going to find lithium on any heat of formation table of values because lithium just exists. Doesn't technically require energy to create because lithium is already made. I'm sure there's going to be a nuclear physicist who's kind of annoyed with that statement, but that's fine. Just consider all the individual elements as made, and we don't have to make them, quote unquote, bunny ears, whatever you want to do. So that should be a big little heads up on your chart. So if you find this chart in your notes, it says the heat of formation of elements and diatomic. So that means oxygen, chlorine, hydrogen, they classify as diatomic. So they also just exist and they do not require any heat exchange to make. Fundamentally, obviously we can make them in the process of other chemical reactions, but to make them themselves doesn't actually require any energy. Again, a little bit wrong with that statement, but if you're actually doing this kind of math, just try to keep that in your head so you don't actually get confused and try to find out where the enthalpy is for, say, chlorine gas. So you'll find this chart somewhere in your notes, and you can see it's got a lot of stuff on there. Keep in mind there's almost infinite number of combinations of chemicals. These are just the very common few that you probably deal with in your physical science class. So it gives you the heat of formation in kilojoules per mole. So you can see there's no units written down next to these numbers. That's because the units are at the top of the chart. So every single one of these values are in kilojoules per mole. You'll notice that a lot of them are negative. So in order to make carbon dioxide, when you add your carbon to your oxygen, you're actually going to release 393.5 kilojoules of energy for every mole of carbon dioxide that you make. So this would be an exothermic reaction. Carbon monoxide releases less energy. Ethane releases less energy. Ethene, right, actually is an endothermic reaction. So it's one of the few on here that are actually endothermic. Most of their chemical reactions, most of the heats of formation on here are exothermic, as you can tell by all the negatives. There's a few that are positive, but by and large, they're all negative. So just pay attention to your symbols. And water is on here twice, once in a liquid state, once in a gas state. So do pay attention to their actual table, their actual values. A lot of students will work through the math and they'll complain after the fact that they keep getting it wrong. And then my first question is usually, is it involving water? And if the answer is yes, I'll then ask, did you use the correct state, gas versus liquid? And then they'll usually look at their work and go, oh, I found my mistake. So just a heads up, when you're doing your work, make sure you're using the correct water. So the steps to do a heat of formation equation, just make sure you have a balanced chemical equation, look for the values on the table, and then just actually carry through the math. So here's the example we're going to go through. It says calculate the enthalpy or the heat of formation of the following reaction using the heat of formation values, table of values. So we have the combustion of propane. Propane, when added to oxygen in ideal conditions, will produce carbon dioxide and water. So once I balance that chemical equation, which by now you should have a pretty good handle on, I should require I didn't write the number in, but 1 mole of propane for every 5 moles of oxygen should yield 3 moles of carbon dioxide and 4 moles of gaseous water. So if I'm going to figure out my overall heat of formation or my overall energy exchange in my chemical reaction, then I need to recognize that I'm doing this equation, which also means I need my table of values handy. I put it, copied and pasted on here, nice and small. Numbers a little hard for me to read, but you should have yours in front of you somewhere. Find all your values. So I color coordinated here. I've got my propane in yellow. So propane is right here, 104.7 kilojoules per mole, negative 104.7 kilojoules per mole. My oxygen is green. So that means hopefully you saw the green little circle here. Remember, it's an element or a diatomic. Oxygen is obviously a diatomic, but it's categorized under this right here. And that means it has no heat of formation value. So there is no enthalpy for it. My carbon dioxide is in orange, so that can be found right here, negative 393.5 kilojoules for every mole. And I'm using gaseous H2O, so gaseous water, which means my overall heat of formation enthalpy value is going to be negative 242.0 kilojoules per mole. So finding your table, your numbers is not that hard. Just have to look at the chart. And then you set up your actual equation. So you want the enthalpy, so the heat of formation values for the products. So my products are on the right-hand side. These are my products. And I have to incorporate my number of moles. So if I have 3 moles of carbon dioxide, I have to take 3 moles multiplied by 393.5 kilojoules. Remember, kilojoules per mole. So you have to incorporate that math. I have 4 moles of water, and therefore I have to multiply by 4 moles. So you're doing a little bit of math there. And then the reactants, well, I only have one value. I have my propane, so I have my 1 mole. There's no number out front, which means I have 1 mole of propane. And so that the reactant side is pretty straightforward. There's only one thing to do over here. So distribute, multiply my moles through, and basically that just cancels out all my moles across the entire equation, which is handy. So then when I actually multiply the 3 and the 4 through, I should get 1,180.5 kilojoules, negative of course, for my carbon dioxide, my 3 moles of carbon dioxide. My 4 moles of water should yield negative 968.0 kilojoules for just to create that much water. And I'm going to have to subtract the energy from my reactants, so my propane. And there's only 1 mole, so I don't really have to do any math for that one other than cancel off the moles. Continue on with your math, just add the products together, and then finally do your heat of formation equation. And so in this chemical reaction, when you actually burn propane, the combustion reaction of propane should yield 2 million kilojoules basically, so or 2,043.8 kilojoules of energy for every mole basically. So because it's a negative, that tells us it's exothermic. And well, I'm sure you guys have barbecued at least once in your life or have seen a barbecue in action. And if it's not a natural gas barbecue, it's a propane barbecue. So I'm pretty sure you've seen that it releases heat energy in order to cook your food. So this one shouldn't be much of a stretch to go, oh yeah, it should be an exothermic. Sometimes it's going to be chemicals you've never heard of before, and you'll have no idea. But you can always just look it up on a chart. And in this case, it is an exothermic reaction because once again, I have a negative symbol for my heat of formation value. So energy was released into the environment, which means the outside surrounding environment gets warmer. And thus, in our case, we could cook food. So this video has gotten a little long. My apologies. You have a few problems, I think 5 or 6 questions. I don't quite remember. Where you have to do your heat of formation. So the assignment starts at the top of the assignment page looks like this, and you are going to do the heat of formation for a handful of them. I don't think I left you that much space, so write small and make sure you have your chart in front of you when you're doing this. And if you have any questions, of course, just fire me an email and I'll help you as best I can.